So we're back, and I'm going to post these all as one continuous playlist, but I took a break here. It's nighttime, which is when my dog gets a little hyper, so you may hear him barking in the background. Uh, so what we did in the last set of videos was we created the TAM coefficient using the generalized partial credit model, assigning credit for the amount of points each home team won against each away team to create a strength coefficient, properly scaled, properly weighted for winning important games, and not weighted as harshly for losing easier games. So at the top of my script here, you'll notice we're back in RStudio because this is where I do everything. And you'll notice I have the first couple lines. I have run the source file that we used in the last video. And that's mostly, I have them in two separate files. I'm not sure why I do that, quite frankly. You probably shouldn't do that if you're a good programmer. But that's what I do. I run this script to make sure I have everything from the TAM file loaded into my workspace. Load the games again. We've got that commented out because you don't need to in the newest file. Run the column names of the games. Here they are. Make sure all the variables are there. Life is good. So there's Mochi. You probably can hear him. I'm not sure. So what we're going to do is create a new variable called skill.n and $home. And what this skill.n $home, it's the row names of skill.n. And just to recap, we've run the line, what skill.n is the skill, the home skill. So we have, again, Sky Blue FC at the lowest and the Seattle Reign at the top. This is the strength of each team at home. This next line just removes the parentheses. Again, I don't want to get too much into the actual R coding, but as you can see, we took the periods out from here to here to make them look like regular words rather than the sort of R language. We're going to merge the games database with the skill database. So what that looks like is this right here. And that's the full thing, so we'll just do the head, the first 6 lines. And here's all our variables. There's the home team, there's the away team, and then there's the skill coefficient added in. Life is good. We're starting to create our full data set here. We're going to create in the tt.s, which, as you remember, is the away skill, the threshold. We're merging the row names in, so then we can merge df games and tt.s by home team. And that gives us, I'm going to run this one more time for you to see, our full df.games. And what this is going to be is our full data set here. So, as you can see as I'm scrolling down in the bottom of the screen, this is all the variables. If we do call names, df.games, it shows you the column names we have. Home, away, home goals, away goals, shots, shots on goal, etc., etc., etc. Life is good. We've got everything in here that we're looking for. The last thing I want to create is an outcome variable. And what that means basically was it a win, a draw, or a loss. And I use a series of nested if-else statements. So if home goals is greater than away goals, then it's a win. And then if home goals equals away goals, it's a draw. Otherwise, it's a loss. Simple. Looks convoluted, but the logic is simple, right? If the home team scores more than the away team, it's a home win. If they score the same goals, it's a home draw. If they score less goals, it's a home loss. Run those real quick, and we get our final df.games. And you can see right here, in the last column, highlighting it didn't really do any good, but so I'll circle it right here. You get win, loss, draw, win. It shows the results. Life is good. I'm going to load a couple libraries. We're actually not going to do the neural network. It doesn't work especially well for this sort of thing. They're really cool. You should actually, anybody interested in machine learning needs to look up the neural network, tries to play Super Mario Brothers. There's a guy who plays video games using a neural network. It's unbelievably cool if you're a big nerd like I am and are super into this stuff. But we are going to load the random forest library. If this is your first time doing it, you have to use the install packages command. But if you've used it before, here you go. I'm going to create a couple variables here: home goals, away goals, outcome. We're going to turn df games $outcome, so this win, loss, draw. We're going to change it from a string to a factor variable. I'm going to hold off on the training and testing right now because the random forest actually doesn't use that method. So we're going to hold off on that. If you do the support vector machine that Matson uses, you do a training testing framework, which I'll talk about, I think, probably toward the end of this lecture. But for this model, we're going to do a random forest. And I've scrolled down to the final model. I did some tuning. I did some playing with it to see what the best predictions came from. But I want to talk about what a random forest is for a minute. And a random forest is basically it's a decision tree model. So think of it as, you have a series of questions, a flow chart almost. You've all seen the flow charts. If yes, then you do something. If no, you do something else. And then you go to the second row, and then, okay, so if yes, and then yes on the second question, then you get to one outcome. If yes, no, different outcome. No, yes, no, no. Get different outcomes each way. And that's effectively what a random forest is. The decision tree model, you would go through all these variables. So if there's 5 shots, 3 of them are on goal. If the skill rating is 5 or something like that, if cat 4 is point whatever, and you go through each of these variables, and you classify each result as a function of these variables. The problem with that decision tree model is it can do what we call overfitting. And what that means is you make it so specific that it's not useful anymore. To use an example from political science, because I just taught this in my data analysis class at Mary Washington, if you're trying to predict if somebody's a Democrat or a Republican, which is something we care about in political science, you could start off with, okay, what is their gender? So men are more likely to be Republicans, women are more likely to be Democrats. And then you go to their income. And someone who makes, X number of dollars is more like, $1 million is more likely to be a Republican. Somebody who makes 30,000 is more likely to be a Democrat. And you take your data set and you train it on each point. And what happens is you have somebody who is a black female Democrat making $37,363 a year in a sales job, who lives in Chicago, Illinois, at this address, at this, you go through it and you get this overly specific prediction that only really applies to one person. It's called overfitting the model. It's so fit to each specific case, it's no longer useful. And that's a problem. You want something where you can predict other cases, and if you do it with the decision tree model, you end up only predicting the cases in your data set. You don't want to be overly specific. You want to group them into bins, what we call it in statistics. And the bigger the bin, the more useful it is. So if you can predict somebody's a Democrat by saying, okay, you are let's say a woman who makes under $50,000 a year, single, age, 25 or younger. That's a good set of predictions right there. That gives us a lot of women are under 25 and make under, I think I said $30,000 a year. There's a lot of women who fit that category. So if we can classify you as a Democrat based on that, it's good. If we need to know you make $30,412 and you're a woman 25 years old, 362 days, that becomes more problematic because there's fewer women who fit that category. The random forest solves the problem of overfitting by only going a few variables deep and then classifying you basically in terms of percentages based on those few variables. So I'm going to show you an example of that right here. I had to install this party package. I'm not sure why it's called party, but because doing random forests is a party. Load the library. You're going to create an object called rf.nwsl2. The only reason is because the model itself is called rf.nwsl. So I just did nwsl2. Creates a tree. Your variable of interest is outcome. And in R for formulas, we do the tilde, and then we do all your explanatory variables with pluses between them. So shots plus shots on goal plus skill plus category 4, which is 100% away points, plus fouls committed, etc., etc., etc. You can read the rest of it. Your data is the DF Games data set, and then we've got some control variables here that we add in. I just basically leave as the default because this is only a teaching demonstration. You never actually want to print one of these trees. But let me show you what you have here. So we run this line, and it creates a tree for us, a single tree. And we plot the tree, and there you go. I'm going to maximize this for you in 1 second, so I'm going to pause, and we will be back.